Segment trees. We are probably familiar with this versatile data structure if we have come across problems that ask us to query a subarray or interval. I recently learned a new and creative way to use segment trees. It's called segment tree beats. If you are unfamiliar with segment trees or lazy propagation in general, please do learn it before watching this video. This is an attempt to make a clear understanding of segment tree beats to someone with just the knowledge of segment tree. This is a three-parter. The first part is a sample problem and its solution. The second part is the proof of complexity, and the last one deals with historic information. Consider this problem. Given an array of size n, we need to perform the following queries. Change ai to minimum of ai and x in some interval for some given x, and second is find the sum of all elements in some interval. Think about it. Pause the video and give it a try. Here we can obviously use the idea of segment tree beats. That's the point of the whole video. Consider this quite often used template for the update function in the segment tree. Here we call this line the break condition, which checks if we should return from this node without performing any operation or not. This line here we call the tag condition, which checks if we should put our tag on the node or not. Tag is the lazy tag. The main motivation behind segment tree beats is that we can change the break and the tag condition according to our needs. We break whenever we want and put tag wherever we want. We can use a stronger or a weaker condition. Give the original problem one more try now, thinking in this direction. What you can do here is, apart from the maximum value, we can also save a strict maximum value inside the interval, and of course the frequency of the maximum value and the sum of the interval. Now we change the break condition. Apart from whether we are inside the interval or not, we also check if the maximum value inside the current interval is lesser than x or not. If it is indeed lesser than x, then obviously no value would be changed inside the interval, because minimum of ai and x is indeed ai for every element in the interval. Now changing the tag condition, we can make it a bit stronger. Apart from being inside the interval, we also want the x to lie between the maximum and the second maximum value. If x is smaller than the second maximum, we go deeper. If x is indeed between maximum and the second maximum, we need to change all the maximum values to x and all the other values remain unchanged. We know that the total sum of the interval would be changed to sum minus f into max plus f into x, where f is the frequency of the maximum value. That is it. This is the sole idea behind segment tree beats. We can now answer queries like update elements as minimum or maximum of ai and x, or find minimum and maximum in a range or sum of a range. Who knew segment tree could do this much? But well, you might ask, what about the time complexity? Won't we visit more nodes during update because of a stronger tag condition? Won't the complexity be greater than just order of n log n? Before answering this question, here is a disclaimer though. The proof is kind of confusing and took me days to properly figure out. So don't be disheartened if you don't understand the proof and watch the video again. Coming back, the answer is no, and here is why. As a footnote, quite unsurprisingly, different tag and break conditions require different proofs of complexity. For now, consider the given problem only. In other words, the given tag and break conditions. Now we have to define some things in order to prove the complexity. We define a mark for each node as the maximum value in the interval that the node represents. And then we remove the mark on a node if it has the same mark as its parent. One can intuitively understand that the total number of marks left in the segment tree would just be the number of distinct elements in the array. Also, another property that emerges is that the second maximum value for a node would just be the maximum value of a mark in the subtree of the node. For a node n, we define u of n as a function that is the number of unique marks in the subtree of the node. And lastly, we define a potential variable p to be the sum of u of n for every node. What is the maximum initial value of p? Since each mark only affects its parents and each node has order of log n parents and there are at most n tags in the segment tree, the maximum value must be order of n log n. We now define ordinary nodes and extra nodes. Ordinary nodes are those which we will visit even in an ordinary segment tree during a range update, while extra nodes are those that we visit thanks to a stronger tag condition. Now coming to the main part of the proof, we analyze how the value of the potential variable changes after a range update. During a range update, we only add a new mark in the ordinary nodes in worst case. But why? Why do new marks only occur in ordinary nodes? Because ordinary nodes are always ancestors of extra nodes, and after an update, the maximum represented by the interval is x. We visit extra nodes only because the second maximum value in the range under the current node is greater than x. So we just visit extra nodes when second maximum is less than x. Also, if we visit an extra node, then its sibling is also necessarily an extra node. Thus, the overall maximum for the two nodes becomes x. And thus, the parent acquires the mark of x, and then we delete the marks on both the extra nodes. Thus, we can intuitively understand that new marks are only added on ordinary nodes, and we always delete marks on extra nodes. Now, one observation that we will now use is that if a mark is inserted in an interval L to R, then only the ancestors of nodes representing L and R are affected. This is because if we look at a node who is not an ancestor of L or R, then either its interval does not intersect with L, R at all, or its interval fully intersects with the interval L, R. In both cases, we will not be adding a mark in its subtree because in first case our break condition helps us, and in the second case it is either an ordinary node which itself will contain a new mark, and there are only order of log n of them, or it will have an ordinary tag as its ancestor, in which case also it will not be affected because a new mark on the ancestor does not affect a node. So we have now established that for a range update, a new tag will only affect the ancestors of L and R and the ordinary nodes which are order of log n in number, and indeed to each one will be added. This is because in a single update, a new mark will have the same value wherever it is added, and since u of n is the function that only counts distinct marks for each node, it will only increase by 1. So yes, this covers the first point. A range query increases the value of the potential variable by log n, so overall it is increased by q log n. Now what about the extra nodes? Earlier we had also established that for every extra node that has a mark, we only visit it to delete the mark. So, for every extra node that has a mark, the value of the potential variable decreases by 1. But what about the unmarked extra nodes? Well, every unmarked extra node we visit is an ancestor of some marked node whose mark we will delete. If there is no marked extra node whose mark is to be deleted, we would not have visited this node in the first place. So, if we deleted the mark of the marked node in its subtree, then we might notice that the u of n for this unmarked node also decreases by 1, because the number of distinct marks in its subtree decreased by 1. So overall, for any extra node we visit in general, the potential variable is decreased by 1. Great. We see that the initial value of the potential variable is order of n log n, and along the queries it is increased and decreased. Overall, the maximum it can increase to is order of n plus q log n, and for every extra node we visited, it decreased by at least 1. So this suggests that the overall number of extra nodes we visited must be less than order of n plus q log n, or else the potential variable will become negative. So we have worked our way through to prove that we visit q log n ordinary nodes and order of n plus q log n extra nodes. So the overall complexity of our segment tree must be order of n plus q log n. Isn't this incredible? But the problem is, as I said earlier, each different tag and break condition requires a different proof. But now we have set a template. This way of thinking about marks and then defining a potential variable and then observing how it changes helps us to get a general strategy to prove the runtime. We just add another type of query to our problem. What if given x, we need to add x to all elements in the given interval? Notice that now the observation we had made earlier that a minimum or maximum update increases the potential variable by log n does not hold for the new kinds of updates. Adding x to an interval can change the number of distinct marks by order of n log n. As an example, consider an array of size 2n where ai equals ai plus n equals I. If I add n to the interval 1 to n, then the value of the potential variable increases by order of n log n. And since there are q queries, the total increase becomes qn log n. And this poses a difficulty as this is worse than the basic brute force, which is order of qn. How do we solve this problem? Take your time, give it some thought, think about redefining the potential variable completely. we redefine the potential variable as being the sum of depths of all marks. Now, initially again the value of the potential variable is order of n log n, as log n is contributed by each mark and there are at most n marks. Now again, we start observing the changes to the potential variable. This time, apart from the mark, the nodes also contain a lazy tag from the add or subtract operations. The interval minimum or maximum operation behaves similarly except for the fact that addition of new mark to an unmarked ordinary node adds order of log n to the potential variable instead of 1 like the previous proof, because the depth of the new mark is O of log n. During interval addition or subtraction, we only visit ordinary nodes and add the lazy tag to them. But how does this affect the marks? What happens to one ordinary node? Firstly, since each of the marks in the subtree of the ordinary node are increased or decreased by the same amount, they will not change at all. Since we only need to consider the worst case scenario, here the worst case scenario happens something like this. Let's say the ordinary node and its sibling are both unmarked but their parent is marked. When we add x to the ordinary node, then its maximum becomes greater than its sibling and hence its sibling acquires a new mark which is just the original maximum and its parent's mark is increased by x. We can also make a similar observation when the value is decreased by x. It should be intuitive as to why this is the worst case scenario. Since a new mark is added in this case, the potential variable is again increased by order of log n. In both queries, each ordinary node adds a value of log n to the potential variable. And in each query, there are order of log n ordinary nodes. So overall increase in potential variable is order of q log square n. Since we only visit extra nodes keeping in mind the lazy tags, during interval minimum or maximum operation, the claim that for each extra node we visit, we delete a mark still holds. And when we delete a mark, the value of the potential variable decreases by log n. But we also had to travel a depth of O of log n to reach the extra node. So we can say that for each extra operation, the value of potential variable decreases by at least 1. Again, since the maximum value of the potential variable over all queries is order of q log square n and each operation for an extra node decreases the value of the potential variable by at least 1, and also the potential variable cannot be negative, so the number of extra operations we did must be order of q log square n. And thus, the overall time complexity of such a segment tree becomes order of n plus q log square n. This might have gotten way too complicated right now, but feel free to rewatch the proof again. As mentioned, the part 3 to this deals with what we call historic information. It's been a common misconception that it has something to do with persistence. But no, it just means that you have to tell the minimum or maximum or sum of all the values of some element at some index that it has ever acquired. This may be a bit confusing right now, but it becomes clear with an example problem. Let's say we are given two arrays of size n, A which contains the original elements and B which has only zeros. And after each query, Bi becomes max of Ai and Bi. There are 5 queries now. First, given x, add x to all elements in that interval. Second, given x, change all elements in the interval to max of ai minus x and 0. Third, given x, change all elements in the interval to x. 4. Given an index, output the element in A in that index. And fifth, given an index, output the element in B in that index. One might notice that B stores the historic information in this case. Bi is the max among all the values Ai has acquired till now. How can this be solved now? Take your time, think about different approaches again. So here, we have to form a relationship between the lazy tags and the historic information. This particular problem is a good example to show how. Here, all 3 updates can be easily described as one function. Let's say we have this function f defined like this. Now, you can easily see that the first query is just this. The second query is just this. And the third query is this. We can just keep lazy tags on the nodes as a pair describing such a function. And also, this function can be merged equally easily. Isn't this amazing? We can now keep these A-B pairs as lazy tags and then easily do a push down and merge the two functions as mentioned. Now coming to the historic information. Maybe we can just maintain the historic value on the leaves? Nope. The lazy tags on the parents might get overwritten again and again, and we might lose a possible maximum value while changing the tags. But we can also maintain a second function as a lazy tag along with f. Call this function h of ai. H of ai will give the maximum value that ai has ever acquired or could have acquired because of some lazy tag that was in that node. Most of the times it's hard to maintain such a function, but in this case it's quite easy. To illustrate this property, here is a graph of a function f. It's just a linear graph after x plus a is greater than b and a constant graph before that. This is only for one particular value of a and b. Let's suppose that the current node has been through many such functions, and among all these we need to see which gives the maximum value always. Obviously, the upper envelope of the set of lines we drew gives the maximum. But observing it, it looks like f, where b is the maximum among all the b's and a is just the maximum among all the a's. So, for each node we can store AB pair for f and CD pair for h, and each time we do a pushdown, we change CD as well as AB. H will be the pair with just the highest values, and we have seen how f works. Initially, in each node A is 0 and B is negative infinity for both f and h, and we change it as we go and solve it in order of log n time. So this is it on how segment tree beats works and how the concept of historic information goes so well with this. If you want to solve some similar problems, the link to the original blog is down in the description. Try some variations on this awesome new way to use segment trees.